Part 1 of Unit 12 is the basics of acids and bases. The first definition of acids and bases we're going to talk about are Arrhenius acids and bases. This is most likely the definition that you already know for acids and bases, but we're going to go back over it. An Arrhenius acid is a substance that, when dissolved in water, increases the concentration of hydrogen ions. And an Arrhenius base is a substance that, when dissolved in water, increases the concentration of hydroxide ions. So, an Arrhenius acid, for example, HCl, hydrochloric acid, when it dissociates in water, it's going to create a hydrogen ion and a chloride ion. An Arrhenius base, for example, potassium hydroxide, when it dissociates in water, it's going to increase the concentration of the hydroxide ion. So increasing hydroxide makes it an Arrhenius base, and increasing the hydrogen ion makes something an Arrhenius acid. The next definition we're going to talk about is the Bronsted-Lowry definition of acids and bases. A Bronsted-Lowry acid is a proton donor. So, for example, nitric acid, HNO3, when we dissolve it in water, we're going to produce H3O+, that's called the hydronium ion, we'll talk about it more in a minute, and the nitrate ion. What happened is this hydrogen was donated to the water to create the hydronium and the nitrate on the product side of this equation. So this hydrogen ion, this proton, was donated to water to create these products. A base is a proton acceptor. So if we look at ammonia, NH3, and it reacting with water, our products in this reaction are going to be the ammonium ion and hydroxide. So in this reaction, what happened is water donated a hydrogen ion, which is the same thing as a proton, to the ammonia to make NH4 and OH. So in this case, our acid HNO3 donated a hydrogen ion, which is just one proton, to water. So it donated, it was an acid, and down here, ammonia, NH3, accepted a hydrogen ion or proton. Remember, those are the same thing, so that makes ammonia a Bronsted-Lowry base. If there's anything that can both donate or accept hydrogen ions, that is said to be amphiprotic. Let me spell that for you. Amphiprotic. And that means something that could be a Bronsted-Lowry acid or base. It can donate or accept protons. Next definition we're going to talk about is Lewis acids and bases. Lewis acids are defined as electron pair acceptors. Atoms with an empty valence orbital can be Lewis acids. Lewis bases are defined as electron pair donors. So anything that could be a Bronsted-Lowry base is also a Lewis base. So if you look in this example down here, ammonia is donating an electron pair to the Lewis acid boron trifluoride. So the boron is accepting the electron pair, that makes it the Lewis acid, and the electron pair being donated by ammonia makes it the Lewis base. So it's kind of the opposite of the Bronsted-Lowry definition. Instead of donating and accepting protons, molecules are going to be donating or accepting electron pairs. It's just flipped on who's doing the donating and accepting. For Lewis acids and bases, acids accept the electron pairs and bases donate the electron pairs. Now earlier I said you need to remember that the hydrogen ion is just a proton, because the hydrogen atom is one proton, one electron, and it's given away that one electron, so all that's left is the one proton. It's often called the acidic proton. In reality, however, that hydrogen ion doesn't exist. It's not just one free-floating proton. all acids are dissolved in water, so that hydrogen ion immediately attaches itself to a water molecule that makes hydronium, and it's got the formula H3O+. So we've got this hydrogen ion, it's going to immediately jump onto a water molecule to create hydronium with a +1 charge. Now, the terms hydrogen ion and hydronium are often used interchangeably. Anytime you see the concentration of the hydrogen ion, that's equal to the concentration of the hydronium ion. They represent the same thing, they're just occasionally written in different ways. Okay, let's talk about conjugate acids and bases. Acid-base reactions always yield a conjugate acid and a conjugate base. An acid donates its hydrogen ion and becomes a conjugate base. A base accepts that hydrogen ion and becomes a conjugate acid. So let's look at the equations from earlier on in this video. We had nitric acid plus water, and it produced hydronium ions and nitrate ions. Now, in this reaction, the hydrogen ion was donated to water. So, this acid donated its hydrogen ion. I'll go ahead and label this as my acid. What is left is called the conjugate base. Now, water, it acted as the Bronsted-Lowry base. It accepted the hydrogen ion or proton, and it became the conjugate acid on the other side of the reaction. So acids become conjugate bases, bases become conjugate acids. So if we were to reverse this reaction and put these things on the reactant side, what would happen is hydronium would act as the acid. It would donate a proton to the nitrate ion. So an acid donates its proton to the base, and whatever's left of that acid becomes the conjugate base. If the reaction were reversed, that conjugate base would act as the base. It would accept the hydrogen ion. The base accepts the hydrogen ion from the acid and becomes a conjugate acid. If we reverse the reaction, the conjugate acid would act as the acid. Remember that the conjugate acids and bases are only going to be things that appear on the product side because they're the result of that hydrogen ion exchange between acids and bases. Okay, so let's look at a couple of acid-base conjugate pairs. We know that hydrochloric acid is a really strong acid. It's one of our 7 strong acids that dissociates completely. Well, when we remove that hydrogen ion, what's left is the chloride ion, Cl-, and see how it says negligible basicity here? Well, a strong acid has an extra weak conjugate base. So this has a very, very low pH. This pH, it's not going to be very high. If we look at a weak acid, like HF, when it gets rid of that hydrogen ion, it's going to become the fluoride ion, and it's a little bit stronger of a conjugate base than chloride is, so a weak acid will have a relatively weak conjugate base. On the flip side, let's look at another weak base. Let's look at ammonia. When it gains a hydrogen ion, it becomes ammonium, and it's got a relatively weak conjugate acid. So we got a weak base forming a weak conjugate acid. When we look at a strong base, though, like let's look at this peroxide ion. When it gains that hydrogen ion, it becomes hydroxide. So actually, the conjugate acid of the peroxide ion base is hydroxide, the thing that makes something a base. So it's got a very extra weak conjugate acid. So the main thing to remember here is that strong acids have really weak conjugate bases, strong bases have really weak conjugate acids, and weak acids and weak bases are going to have weak conjugate acids or bases. Okay, your question from this section: what is the conjugate acid formed in the following reaction?